Hello students, today we are going to discuss about magnetic effects of electric current for the revision purpose. Okay, so what is magnetic effects of electric current? Before that we already studied has heating effect of electric current. When electric current pass through a conductor, the temperature of the conductor rises, that is known as the thermal effect or heating effect of electric current. So today we are going to discuss about another effect of electric current, that is known as magnetic effect of electric current. So it was first observed by Oester. Oester observed that when there is a current carrying conductor is placed and he placed a compass or magnetic needle close to it, the magnetic needle gets deflected by this current carrying conductor. So as there is, we already know that a magnetic field get deflected only because of an external magnetic field, and except the current carrying conductor there is no other substance. That's why he concludes that the current carrying conductor is able to produce a magnetic field. This is known as what? Magnetic effects of electric current. And the deflection of the magnetic compass or needle can be obtained by using Amperes Amperes swim rule or by snow rule. What is Amperes swim rule? If a swimmer is swim along this direction of the current flow, so that the current enters at its leg and comes out from his head, then the left hand of the swimmer will shows the deflection of the north pole of the magnetic compass. Or what is snow rule? When a magnetic compass placed parallel to the current carrying conductor such that the current through the compass flows from south to north direction. If current flows through the conductor in such a way that if we place the magnetic compass parallel to it, so that the current through the magnetic compass pass from south to north direction, then the north pole of the magnetic compass deflects towards west direction. That is known as snow rule. So by the application of snow rule or Amperes swim rule, we can get the direction of deflection of the magnetic compass which is placed close to a current carrying conductor. And the deflection of the compass also depends upon the intensity of the current flowing through the conductor. If the current is more, the deflection will be more, and again if the direction of the current flowing through the conductor will change, the deflection of the compass also get changed. So it was first observed by Oester, who states that according to his experiment that a current carrying conductor is able to produce a magnetic field surrounding it. Then we have to study what is Biotsavarts law. So according to Biotsavarts law, if a current carrying conductor is able to produce magnetic field surrounding it, then what will be the strength of that magnetic field? So according to Biotsavarts law, if there is a current carrying conductor which carries current I, then if we are considering a small segment of the current carrying conductor of length dl, due to which we have to find out the magnetic field strength at a point P which is at a distance r from this current small segment which is known as current carrying element. This small segment carrying current I dl is known as current carrying element. So due to this current carrying element, the magnetic field strength at this point, according to Biotsavarts law, is defined as the magnetic field strength dB is directly proportional to the current carrying element and directly proportional to the sine of angle between the direction of current carrying element and the position vector of this point of observation with respect to the current carrying element, and inversely proportional to the square of distance of the point of observation from the current carrying element. So what is the direction of current carrying element? The direction of current carrying element is always tangent to the current carrying conductor at the point where we are considering the current carrying element. As here I am considering the current carrying element, its direction will be tangent to this, and this is the direction of position vector of the point of observation P. So this angle here will be theta. So combining this, we can write dB is proportional to I dl sin theta divided by r square, or if we remove the proportionality symbol, it will come to the constant which is mu naught by 4 pi into I dl sin theta divided by r square. This is the scalar form of Biotsavarts law, or if you can write it in vector form, it will be written as how much? dB vector will be equal to mu naught I by 4 pi into dl vector cross r vector divided by r vector magnitude cube. This will be the vector form of Biotsavarts law, where dB is the magnetic field strength at this point P due to this small current carrying element. If we want to calculate the complete current carrying conductor, we have to integrate this. Clear? Okay, so this is the expression for what? Biotsavarts law. Okay, and its direction or the direction of magnetic field can be obtained by using right hand palm rule or right hand thumb rule. Right hand palm rule, if I am stretching the finger of the right hand along the direction of r vector, and the thumb along the direction of current carrying element, that is dl vector, then the palm will shows what? The direction of magnetic field. So as here this is the direction of r vector, so I am stretching the finger along r and thumb along dl, so the palm is into the plane or board, so here the magnetic field strength is into the board. Okay, so now what is the application of Biotsavarts law? So for a infinite long straight current carrying conductor or a finite long straight current carrying conductor, if this is a long straight current carrying conductor carrying current I, and here is a perpendicular distance of point of observation P, which is R, the end A and B be the two ends of this current carrying conductor. This end A makes an angle theta 1 and the end B makes an angle theta 2 with this perpendicular distance r. Then the magnetic field strength at this point P will be how much? The formula will be, the magnetic field strength at point P will be mu naught I by 4 pi r sin theta 1 plus sin theta 2. Clear? Here theta 1 is this angle which is measured in clockwise direction, and theta 2 is this angle which is measured in anti-clockwise direction. So according to the sense of measurement, you have to put their symbol plus or minus. So this is the formula for magnetic field strength at this point P due to this finite long straight current carrying conductor. If it is infinite conductor, so the length will be infinite. This is the point of observation P at a distance r, and it carries current I. So if the length is extended up to infinite, so these two angle will be how much? If it is up to infinite, so these angle will be 90, this theta 1 theta 2 both will be 90. So for infinite conductor, theta 1 equal to theta 2 both are 90. So what is magnetic field strength at point P? Mu naught I by 4 pi r sin 90 plus sin 90. So it will become how much? Mu naught I by 2 pi r, because sin 90 is 1. Okay, so if it is semi infinite, that means if the point of observation is close to at one end, this is extended up to infinite, here the point of observation is close to at one end at a distance r. Then for this point of observation carries current I. So what is the magnetic field strength at point P will be mu naught I divided by 4 pi r into, here sin theta 1, this angle will be how much? 90 degree, and theta 2 to this end will be 0. So here theta 1 is 90 and theta 2 is 0. So sin 90 plus sin 0. What is sin 0? Sin 0 is 0. So this will be mu naught I divided by 4 pi r. So this is the expression for magnetic field due to infinite long straight current carrying conductor when the observer is close to one end. If the point of observation lies along the length of the conductor, let this is a point of observation P dash which is at a distance r, but lies along the length of the current carrying conductor, then for this case theta 1 will be 180 and theta 2 will be 0. So for this, if P dash is along the length of the conductor, then the magnetic field strength BP will be 0, because theta 1 equal to 180 and theta 2 equal to 0 degree. Okay, you have to remember all these formulas, and for the derivation you can refer to the previous lecture. Next, the application for Biotsavarts law for finding out the magnetic field strength at the center of a circular coil. So if here is a circular coil of radius r and carries current I in anti-clockwise direction, so what will be the magnetic field strength at this point O? So let us consider a small segment of length dl. So here the direction for current carrying element will be this, always tangent to the segment. So the angle between current carrying element and position vector will be 90. So here at P it will be magnetic field strength O due to this small segment will be I dl sin 90 divided by the distance is r square into mu naught by 4 pi. So this will be how much? I dl by 4 pi r square into mu naught. So the complete segment will produce how much magnetic field strength? So by integrating this, so here dl is the variable. So dl is vary from 0 to complete length of the ring, that is 2 pi r. So this will be I mu naught divided by 4 pi r square is taken as common constant 0 to 2 pi r dl. So this will become I mu naught by 4 pi r square into 2 pi r. So 2 pi will cancel, r will get cancelled. So it will be mu naught I divided by 2r. So this is the net magnetic field strength at the center. Clear? So if it is a semi, or if we want to find out for any circular arc like this, if this is a circular arc, here it's make an angle theta and the radius is r and it carries current I. So for this segment at O, so magnetic field strength at O due to this circular arc will be mu naught I by 4 pi r into theta. Okay, you have to remember this formula. For the derivation you can refer to the previous lecture. So for any circular arc at the center which makes an angle theta with the center is mu naught I by 4 pi r. R is the radius of the current carrying circular arc and theta is the angle made by the arc at the center. Clear? So next, and its direction can be obtained by, this is the direction of current carrying element dl and this is the direction of position vector. So the palm will show the magnetic field strength and here the magnetic field is into the plane. Or right hand thumb rule, if I am crawling the finger along the direction of current, the thumb will show the magnetic field at this point O. Okay. Next, what is the magnetic field strength due to a current carrying circular coil at the axis? If this is a current carrying coil which carries current I and this is the radius r, and here is a point of observation P at a distance x from its center. So what is the magnetic field strength at this point? So here the magnetic field strength due to this current carrying circular coil at a distance x will be how much? Mu naught I r square divided by 2 into r square plus x square to the power 3 by 2. This is the expression for the magnetic field strength at this point P due to this complete circular current carrying coil, where r is the radius and x is the distance of point of observation from the center O. If this x is very close to the center, that means if x is very negligible in comparison to r, so you can neglect x with respect to r. So what is BP? Mu naught I r square divided by 2 into, we can neglect x in comparison to r, so it will be r cube, because x tends to 0, so r cube it will become how much? Mu naught I by 2r. So if the position is very negligible in comparison to r, so we can consider it as the center of a circular loop. This is the expression for it. Okay, and the direction can be calculated considering derivation. You can refer to the previous lecture. Next, we will study what is Ampere's circuital law. So according to Biotsavarts law, we are able to find out the magnetic field strength due to a current carrying conductor or loop. Okay. So now what is Ampere's circuital law or Ampere's law? So Ampere's law states that the line integral of magnetic field strength over a closed loop will be mu naught times of the total current enclosed by that loop. That means B dot dl closed in line integral is equal to mu naught I enclosed. Okay, if here is a current carrying conductor which is carrying current into the plane, and here is a point of observation P. So the magnetic field at point P due to this current carrying conductor will be how much? I have to assume a closed loop over this point of observation P. Let this distance be r. So the magnetic field strength at this point P will be how much? B at P dot dl. Dl is over closed integral, will be mu naught into total current enclosed by this loop. What is the current enclosed? Only this current I, so it will be I. So B at P will be how much? Closed integral of dl mu naught I. So closed integral of dl will be the complete length of this loop, will be how much? 2 pi r. So B at P into 2 pi r is equal to mu naught I. So B at P equal to mu naught I by 2 pi r. Clear? So this is known as Ampere imaginary loop is known as Amperian loop, and this is the application of Ampere's circuital law, which gives us the closed line integral of magnetic field strength over a closed loop will be mu naught times of the total current enclosed by that loop. Okay, and in this formula or this expression, this B is due to all the current carrying conductor present over there, and I is only the current which is enclosed by this Amperian loop. For example, if there are large number of current carrying conductors carrying I1, I2, I3, I4, there are 4 current carrying conductors of different directions, and I want to find out the magnetic field strength at this point P. So here I am considering a Amperian loop like this, which is at a distance r from this. So for this loop, these two are only the current enclosed, but these are also the current carrying conductors present over there. So the magnetic field strength at this point P, if I am applying Ampere and circuital law at this point, so B at P dot dl will be equal to mu naught into I enclosed. What is I enclosed? These two current carrying conductors, or these two currents only, because these two currents are enclosed by this loop. So it will be I2 plus I4, because both are in same direction out of the plane, but these two are not the current enclosed by this loop. But this magnetic field strength P at this point will also due to this one and all these current carrying conductors. So in Ampere's circuital law, the magnetic field will be due to the all current carrying conductors present over that surface, but the I enclosed is only the current that enclosed by the imaginary Amperian loop. Okay, you have to remember this point. Next, the application of Ampere's circuital law. So by the application of Ampere's circuital law, we can find out the magnetic field strength due to a cylindrical current carrying conductor if this is a hollow cylindrical current carrying conductor which is extended up to infinite or for some finite length L. So if as it is a hollow current carrying conductor, it carries current only the surface, because within the conductor there is only space, so current flows along the surface only. So I have to assume 3 points. One is on the surface, let 1, another is out of the surface 2, another one is inside the current carrying conductor 3. So for these 3 points, we have to assume the magnetic field strength by using Ampere's law. So first of all, we have to assume a Amperian loop if I want to find out the magnetic field at 1. So I have to assume a Amperian loop over that point of radius r. So by applying magnetic Ampere law, B at 1 dot dl closed integral into mu naught I enclosed. What is I enclosed? As this is a hollow cylindrical, all the current are flowing along the surface of the conductor only, and that will be the same as that of the complete current carrying by this conductor, that will be I. So this will be how much? B1 closed integral of dl into mu naught I. What is closed integral of dl? The complete length of this Amperian loop, that will be 2 pi r. So B1 into 2 pi r equal to mu naught I. So B1 will be how much? Mu naught I by 2 pi r. Similarly, if I have to assume the magnetic field strength at point 2, I have to assume Amperian loop. Let this distance be r. So by applying, we will get B at 2 will be how much? Mu naught I divided by 2 pi r. But at point 3, which is within the conductor, there is no current enclosed within this Amperian loop, because all the currents flow on the surface of the Amperian loop. Within it there is no current flowing, so I enclosed will be 0. So B at 3 will be 0, as I enclosed equal to 0. Clear? So here we have to assume an Amperian loop in such a way that the direction of magnetic field at each and every point of the Amperian loop and the dl vector will, okay. So if the conductor is hollow, then there will be no current within the conductor. That's why for the case point 3 there will be no I enclosed within it, so the magnetic field strength at point 3 will be 0. But if the conductor is solid and the current I which is flowing through this conductor is uniformly distributed over throughout the cross sectional area, then for this point 3 the I enclosed we have to calculate it. What is the I enclosed? As we already given that the complete I is flowing over the complete cross sectional area of the conductor which is of radius r. So for this small r dash radius which is at point 3, the I enclosed will be how much? I3 enclosed will be how much? Total current divided by total cross sectional area or the current density, that is pi r square into the area of this small cross sectional area across which we have to find out the magnetic field strength would be pi r dash square. So it will be how much? I r dash square by r square will be the I enclosed. So B3 for this, if the conductor is solid and current is uniformly distributed, will be how much? Mu naught. What is I enclosed? I enclosed will be I r dash square divided by r square into 1 by 2 pi r dash. So it will be r dash will get cancelled. So mu naught I r dash divided by 2 pi r square will be the expression for magnetic field strength inside the solid current carrying conductor. But for the case 1 and 2 the expression remains same because the complete current will be the enclosed current for these 2 Amperian loop. Okay, and here you have to remember that the Amperian loop have to choose in such a way that the direction of the Amperian loop and the magnetic field strength at each and every point should be same, and the value of the magnetic field strength at each and every point on the Amperian loop will be equal. Okay, so next we have to apply the Ampere's circuital law for find out the magnetic field strength due to a ideal solenoid. What is solenoid? A large number of turns which are closely wounded to each other such that the coil have larger length in comparison to its radius. So if this is the length of the solenoid and this is the radius of the solenoid such that R is very negligible in comparison to L, then it is known as an ideal solenoid. If current is flowing through it I and N be the number of turns per unit length, then what is the magnetic field strength due to this solenoid? So for this we have to assume a Amperian loop like this. Let us consider a rectangular Amperian loop P Q R S. Okay, so for this rectangular Amperian loop, if this is the length small l with the length of the Amperian loop, so we have to find out the magnetic field strength by applying Ampere's circuital law. So for this B due to this segment S R dot dl closed integral plus B due to the segment RQ B due to RQ dot dl plus B due to QP dot dl plus B due to PS dot dl will be equal to mu naught I enclosed. Clear? So from this, if this is the Amperian loop, the direction of dl is along this and the magnetic field strength are also along this, so it will be B. What is dl? dl will be the length of the conductor L plus here this will be 90 degrees, so it will become 0, and for this outside the solenoid the magnetic field strength is 0, so for this term will also become 0 and this will be become how much? Again 0 because this is 90 degree is equal to mu naught. What is I enclosed? The length is L, number of turns per each length will be small n, so total number of turns will be n into L into current carrying by each turn will be I, so total current enclosed by this much Amperian loop will be mu naught NLI. So NLI will be the total current enclosed by this Amperian loop. So from this we will get B, inside it will be mu naught NLI divided by L, which will gives us B equal to mu naught NI. So this is the magnetic field strength due to a solenoid within it. outside it will be 0, and you have to remember that the magnetic field strength at the two ends of the solenoid will be half of this. So B at end of solenoid will be mu naught Ni by 2. Okay, similarly for case of toroid, so in this case if current I is flowing through it, so we have to assume 3 points, point 1 within the toroid, point 2 inside the toroidal core, and point 3 outside the toroid. So for these three cases the magnetic field at 3 and 1 will be 0, because at this point if the current is going out of the surface, if like this it is going into the surface, and all these points it's going out of the surface. Okay, so if I am considering a point here and a Amperean loop like this, so the net current will be 0, because same amount of current going into the plane and same amount of current coming out of the plane. So I enclosed for point 3 will be 0, so the magnetic field strength will be 0. Similarly for point 1, if I am consuming a Amperean loop, there is no current enclosed within this Amperean loop, so the magnetic field strength will be 0. But if I am considering the point 1, then there will be only one type of current which is going into the plane, that is will be I into total number of turns, and it will gain same as that of the magnetic field strength at point P. Point 2 will be mu naught Ni. Clear? Same as that of solenoid. Clear? So this is how we can apply the Ampere's orbital law to find out the magnetic field strength due to a solenoid and due to a toroid at different point and due to a cylindrical current carrying conductor at different places. Clear? And next we will study when there is a charge, magnetic force on a moving charge. So you already know if a charge is at rest, then there will be no effect of magnetic field on it, but when a charge is moving with certain velocity, then the magnetic field can apply a force on it, and the magnitude of that force is depends upon q v b sin theta. This is the magnetic force acting on a moving charge, where q is equal to the charge, v equal to velocity of the charge, b is equal to the external magnetic field strength. This is magnitude of velocity. Okay, magnitude of velocity of the charge, external magnetic field strength, and theta is the angle between velocity vector and magnetic field strength vector. Clear? And the direction of the force can be obtained by using right hand palm rule. If I am stretching the thumb along the direction of V and fingers along the direction of B, then the direction of palm will show the direction of force if there is a magnetic field which is acting into the plane. Okay, and the charge Q is moving along this direction with velocity v, then the direction of force will be obtained by using right hand palm rule. I am stretching the thumb along the direction of v and fingers along the direction of b into the plane, so the palm will show the direction of force, so the force direction will be like this. Okay, clear? And its magnitude will be this much. So from this expression we get if theta equal to 0 or 180, theta equal to 0 or 180, then f equal to 0. That means if the charge moving in external magnetic field of strength b in such a way that the angle between magnetic field strength and velocity vector is 0 or 180, either the charge moving along the direction of magnetic field or opposite to it, then the force acting on it will be 0. And if theta equal to 90, the magnetic force will be maximum, which is equal to qvb, because sin 90 is 1. So this is the maximum magnetic force acting on a moving charge when the angle between direction of motion or velocity of the charge and magnetic field strength will be 90. So as from this case we get that, or the vector from the formula for this will be the magnetic field strength will be q into v cross B. So from this expression we get the magnetic force is always perpendicular to V cross B. As this is a cross product, this resultant is always perpendicular to this or the plane containing V cross B. That means the force is always perpendicular to velocity. That means the force is perpendicular to the displacement. So the magnetic force does zero work. Okay, as it is always perpendicular to the velocity. That means it is always perpendicular to the displacement. That's why it does zero work. Okay, and as the force is always perpendicular to V cross B, so when the angle is 90, the force is maximum, and this force due to this force the charge starts to moving along a circular path, because for each and every instant the force is always perpendicular to the direction of velocity, like this. If this is the direction of velocity, the force is acting on this 90 degree. So at each and every point it will start acting on it in perpendicular direction, so the charge will start rotating in a circular path. So what will be the radius of that circular path? So in this particular case, the required centripetal force, as we know, for the rotation of a particle in a circular path, centripetal force is necessary. So for this case, the required centripetal force, if the circular path have radius r, so mv square by r will be equal to qvb, because the required magnetic force here provides the centripetal force. So from this we will get r equal to how much? mv by qb. So when the angle between magnetic field strength and velocity vector is 90, the charged particle starts to revolve in a circular path with radius this much. You have to remember this formula. From this we will get the time period, as it is continuously revolving in a circular path. So what is the time period? Time period will be total distance by velocity, 2 pi r by v. So from this we will get 2 pi m by qb. Or in place of r we can write how much? 2 pi into mv divided by qb into v. So v will get cancelled, it will 2 pi m by qb. So from this we will get the frequency will be 1 by t, which is equal to qb by 2 pi m. Okay, and what is the angular frequency? Omega equal to 2 pi f. So this implies omega will be how much? qb by m. Okay, you have to remember all these formulas. When a circular, when a charged particle moves in a circular path due to a magnetic force, what is its radius, what is the time period, frequency, and angular velocity or frequency. Clear? And this is the application that we used in case of cyclotron. What is cyclotron? Cyclotron is a particle accelerator in which there is two D's present close to each other and a magnetic field is acting. Case of cyclotron, there are two D's which are close to each other and magnetic field acting perpendicular to it, like this, and these two D's are connected with a alternating EMF source, so that the electric field which is exist between these gaps will change alternatively. That's why if a charged particle is placed over, it will start revolving in a circular path repeatedly, and gradually its velocity increases, and finally it gets accelerated and then get out of the D's in a path which then it will hit a target. This is the concept of cyclotron, but this is not in your syllabus, so you don't need to go through in details, but if you want then you can refer to the previous lectures. Okay, so next, if the charged particle moving at an angle theta, that means there is a angle theta between the magnetic field and velocity, like this. If here is the magnetic field strength B and a charge Q is moving along this direction with velocity V, and the angle between V and V will be theta, then for this case what will be the expression? As this charge is moving along this direction and the theta is the angle between B and V, so the velocity have two components, one is V cos theta along B and another one is V sin theta, which is perpendicular to the direction of B. So due to the component V sin theta, as this V sin theta component of the velocity is perpendicular to the direction of magnetic field, for this component the charged particles will start revolving in a circular path, but due to the component of V cos theta, it wants to move in a linear path. So as a resultant of these two, the charged particle will travel in such a path which is known as a helical path or helix. Clear? And in this case, what is the radius of this helix? We can write the radius, the circular path is due to the V cos theta, so the radius will be V sin theta is the cos, so V sin theta by QB will be the radius. And similarly you can find out the time period, frequency, or anything that you want regarding this. And what is M? M is the mass of this charged particle. Clear? And due to the v cos theta, the charge moving in a straight line. What is the time period for this? T equal to 2 pi m by qb, which is independent of velocity. So the for time period, in one time period or in one cycle of the charge particle, the linear distance covered by that charge particle will be known as pitch of the helix. Okay, so in one time period, what is the linear distance covered by the charge particle is known as the pitch of the helix. So what is pitch? So the linear velocity is v cos theta and time period is 2 pi m by qb. So pitch equal to v cos theta divided by qb into 2 pi m. This is the value of the pitch of the helix. So you have to remember this formula, and this is the radius of the helix. So when charge particle move at any angle with the magnetic field, then it will move in a helical path. This is the radius of the helix and this is the pitch of the helix. Clear? So this is how a charge particle experiences a force when it moves in a external magnetic field. Okay. Next, we will study the magnetic force acting on a current carrying conductor. So as we already know, if here is a current carrying conductor, current flowing through this conductor and it is present in an external magnetic field. So as we previously discussed right now, that a single charge will experience a force F equal to Q into V cross B, and the direction will be obtained by applying right hand palm rule. So here a current carrying conductor means it carries a large number of charge which is flowing across it, and each charge will experience this much force. And in this case, as current is flowing through the conductor, all the charge particles are moving with a velocity which is equal to drift velocity. So each single charge will experience a force equal to minus E into Vd cross B, because if current is flowing along this direction, all the free electrons inside the conductor will drift opposite to that of direction of current. So this will be the force experienced by a single charge. If the total number of charge we have calculated, or the charge density per unit length will be N and the length of the conductor will be L, so the total number of electrons will be N, L into cross sectional area is A, will be A into this much force. If I am assuming another vector quantity which is along the direction of current, that is L vector, and its magnitude equal to length of the conductor, then we can replace Vd minus Vd vector with respect to L, because L is the magnitude same as that of A length and its direction is opposite to Vd. So we can write NAE Vd into L vector cross B vector. So this will become, this term is NAE Vd known as I, so it will be I into L cross B, or the force on the current carrying conductor F will be how much? ILB sin theta. And this direction of the force can be obtained by using right hand palm rule. The thumb along the direction of length or a current, because this shows the direction of length shows by the direction of current. So thumb along the current, fingers of the right hand along B, then palm will shows the direction of force, as in this case the force will be along this direction. And the magnitude of this force will be this much, ILB sin theta. So when theta is 0, that means if the angle between L vector and B vector are 0 or 180, the force will be 0. That means if the current carrying conductor lies along the direction of magnetic field strength or opposite to it, the force acting on it will be 0. If it is perpendicular to it, theta is 90, then the maximum force acting on it will be ILB. Okay? Clear? And in this formula, that is the force acting on a current carrying conductor, magnetic force is I into L cross B. L is the displacement vector between initial and final position of the current carrying conductor only when the magnetic field strength is uniform. That means if the strength all over this place is uniform and there is a conductor like this of length L, or any arbitrary shape of conductor having initial and final position at A and B, then from this the length of this will be the displacement vector from initial to final position. If this is the direction of current, this will be the value of L. So you have to find out the displacement between initial and final position, which will replace the L value if the magnetic field strength all over there will be uniform. Clear? So by this concept, you can find out the magnetic force acting on any arbitrary shape of current carrying conductor until the magnetic field strength all over there will be uniform. Clear? What is next? What is the force between two parallel current carrying conductors? If there are two parallel current carrying conductors carrying current I1 and I2, so the I2, or this is the one current carrying, this is the two current carrying conductor. If the current carrying conductor 2 is placed in the magnetic field of I1, so here the magnetic field is B1 which is acting into the plane. So what is the force acting on 2 due to 1? It will be ILB, I2 L2 B1 angle. This is the current direction, magnetic field into the plane 90, so side 90 will be 1. This is the force of the I2. What is B1? If this is the distance is R or D. So due to an infinite current carrying conductor, the magnetic field strength at a distance D will be mu naught I by 2 pi D. So it will be mu naught I1 divided by 2 pi D into length. As this is an infinite length, so we have to find out the force per unit length. So it will be L. So the force per unit length will be mu naught I1 I2 by 2 pi D. Similarly, if I am find out the force on 1 due to 2, here the magnetic field will be due to 2, that is out of the plane. If I am applying right hand thumb rule or right hand palm rule, current along this direction, position along this direction, so palm will be outward, so here the magnetic field will be out of the plane. So what will be force on 1 due to 2 per unit length will be mu naught I1 I2 divided by 2 pi D, same as this one. But the direction for F1 and F2, here the field is into the plane, current is along this, so the force along this direction, this is the direction of force on 2 due to 1. Here the field is out of the plane, current is along the direction, so force will be along the this direction, force on 1 due to 2. So when current flowing along two parallel current carrying conductors along same direction, the force is attractive or they attract each other. But if the current will be in opposite direction, they will be repel each other, but the magnitude of force per unit length will be same, that is mu naught I1 I2 divided by 2 pi D. Clear? You have to remember this, it may ask in your examination. And for the complete derivation, you can refer to the previous video lectures. Next, a current carrying loop present in an external magnetic field. So when a current carrying loop is present in an external magnetic field, if like this, it carries current I along this direction and this is the direction of magnetic field, then the net force acting on it will be 0, F net equal to 0, but it will experience a torque due to, we already derived these two forces will rotate it and these two forces will cancel each other. So it will experience a torque, and what is the torque due to this? That will be BINA sin theta, or this can be written as in vector from M cross B. This is the torque acting on a current carrying loop. And what is M? M equal to N I into A, N equal to number of turns of the coil, A equal to cross sectional area of the coil, I current flowing through the coil, okay, and this complete M is known as magnetic dipole moment of the current carrying coil, and B is the external magnetic field strength. Clear? So from this we will get tau equal to BINA sin theta. What is theta? Theta is the angle between area vector and magnetic field strength. Okay, clear? So this is when a current carrying coil is present in an external magnetic field of strength B, it will start rotating due to a torque which is given as BINA sin theta. For the derivation, you can refer to the previous lecture. And the net force acting on a current carrying coil in a external magnetic field is always 0. Okay, so as we already discussed that if there is a current carrying coil present in an external magnetic field, it will experience net zero force but a torque which is equal to BI sin theta or M cross B, where M equal to NIA, the magnetic dipole moment of the current carrying coil. And we can find out the direction of force acting on a current carrying conductor by using right hand palm rule. Okay, or there is another law by using which we can find out the force acting on a current carrying conductor or a moving charge particle, that is known as Fleming's left hand rule. So according to Fleming's left hand rule, if the first finger of the left hand, you have to stretch 3 fingers of your left hand, thumb, first finger and middle finger perpendicular to each other in such a way, if the first finger shows the magnetic field direction, then the middle finger shows the direction of current, thumb will shows the direction of force. Clear? This is known as Fleming's left hand rule. You can use this to find out the force acting on a current carrying conductor or a moving charge in an external magnetic field. Clear? So next we will study now we already studied that a moving charge can experience a force due to an external magnetic field, and a current carrying conductor also experience a force, but when there is a closed loop which carries current, it experiences zero force but it will experience a torque which given as formula M cross B. Next we have to study that by this concept of current carrying conductor experiencing a torque, we used a most important instrument in each and every circuit, that electrical circuit, that known as a galvanometer, or it is known as moving coil galvanometer. So in moving coil galvanometer, as a moving coil galvanometer, there is 2 strong magnets, cylindrical magnets, due to which the magnetic field within it will be radial, and a cylindrical soft iron core is there on which a coil is wrapped. Okay, this is the top view. The coil is wrapped over the coil, and if I am supplying a current, it has a marker like this, and from this the spring will be attached. The diagram will be like this. Here are 2 magnets, north south. Here is a T head, here is 2 terminals. A coil is wrapped over here with a hairspring. One end is connected to this terminal and another end is connected to this terminal over a soft iron core. So when current flowing through it, it starts rotating due to the magnetic field. And due to this rotation, this hairspring will get rotated. So at equilibrium state, as the radial magnetic field is always along the direction of area vector, so torque will be always maximum, that is BINA. Because theta is always 90. So this is BINA, the maximum torque, which is equal to C theta, the restoring torque by this hairspring. So theta is the what is theta is the deflection or the rotation, angular displacement of the spring, and C is the torsional constant. So from this we will get the current I equal to C theta divided by BNA. So from this we can write psi is directly proportional to theta, where C by BNA is a constant which is known as galvanometer constant for a given galvanometer. For C is constant because for a given galvanometer C is constant, magnetic field, the magnets are constant, number of turns of the coil is constant, cross sectional area of the coil is constant. So this is known as galvanometer constant. So from this I is directly proportional to theta. Okay, this is known as galvanometer constant. Okay, and for the detailed derivation you can go through the previous video lectures. So this is the condition when the coil will comes to equilibrium condition. That means the torque due to the current and the restoring torque due to the angular disturbance of the coil become equal. This is the restoring torque, this is the deflecting torque, become equal. The coil becomes to equilibrium and it will again regain its initial position by this condition, and this is the constant which is known as galvanometer constant. So from this we can get the voltage sensitivity and current sensitivity. What is current sensitivity of a galvanometer? The current sensitivity of a galvanometer is the deflection shown by the galvanometer per unit current flowing through it. Okay, that is theta by I is known as the current sensitivity. Similarly, what is voltage sensitivity? The deflection shown by the galvanometer per unit potential supply difference supplied across the galvanometer. So what is potential difference? Theta into I into R. What is R? R is the resistance of the galvanometer and current I is flowing through it, whose value will be this much. Clear? So this is known as the current sensitivity, this is known as voltage sensitivity of a galvanometer. You can find out the expression by using replace by I with this much here and here. Clear? Next, how to convert a moving coil galvanometer into a ammeter and voltmeter. We already studied that a moving coil galvanometer can convert it into an ammeter by connecting a very small resistance which is known as shunt in parallel to it, and it can convert it into a voltmeter by using a very high resistance R in series to it. Clear? And an ideal ammeter have resistance 0 and an ideal voltmeter have resistance infinite. Clear? So in case of conversion of a galvanometer into an ammeter, shunt, small resistance in parallel to it, connected in parallel to it, but when a galvanometer is converted into a voltmeter, high resistance, connected in series to it. You have to remember this, and for further details you can refer to the previous video lecture. Clear? So this is how galvanometer works on the concept of torque acting on a current carrying conductor. This is the principle of a moving coil galvanometer in which a current carrying conductor placed in an external magnetic field experiences torque. And what is the galvanometer constant? How a galvanometer converted into a ammeter and voltmeter? What is voltage sensitivity and current sensitivity of a galvanometer? Clear? So next we will study So next we are going to study that we already here discussed that a moving charge placed in an external magnetic field will experience a force, that is Q V sin theta or Q into V cross B. But what is Lorentz force? So Lorentz force is the net force when a charged particle moving in a field where both electric and magnetic field are present. Okay, if this is the direction of magnetic field and this is the direction of electric field, and a charge Q is moving along this direction with velocity V, then the net force acting on it will be the force due to the electric field, that is QE, plus the force due to the magnetic field, that is Q into V cross B. And this net force is known as the Lorentz force, which is acting on a charge moving in a field, because a moving charge in an external magnetic field and electric field will experience force due to these two. If velocity of the charge is 0, it will experience 0 magnetic force, but a force due to electric field is there. Clear? So this net force is known as the Lorentz force, which is acting on a charge which is moving in an external magnetic field and electric field, because electric field and magnetic field are both interlinked with each other, they are not independent of each other. For example, if here is a current carrying conductor, it is able to experience a magnetic field surrounding it. We already studied. So if here is a charge Q which is moving along this direction with velocity V, the magnetic field is into the plane, let be the strength be B, so it will experience a force due to the magnetic field which is equal to Q into V cross B, and this direction will be along this direction, so it will get deviated along this direction. But for the same case, if the charge is at rest, velocity will be 0, so it will experience 0 force. because there is no electric field produced due to this current carrying conductor. But if there is another observer which is moving in a lift, let the observer 2 along this direction as that of the motion of the charge with same velocity v, then for this observer O2 the charge q is at rest, although it is moving with a velocity v, but the same velocity is for the observer O2. So for O2 the charge q is at rest, but still it gets deviated along this direction. So from this we will get what? The force which is a magnetic force due to a observer 1 which is at rest, for which the charge is moving with velocity v, is a magnetic force. But for the observer O2 which is moving with velocity v as that of the charge, the force is a electric field force, because here the charge is at rest but still it gets deviated. So the field which is magnetic for observer 1, the same will be electric for observer 2. So both magnetic and electric field are interlinked with each other. That's why in generally the force acting on a charge is the Lorentz force, but we studied it separately. But actually this net force acting on a charge is the Lorentz force. Maybe sometimes it is due to only electric field, or sometimes it is only due to the magnetic field, or sometimes it is due to both of these. So this is known as the Lorentz force, which will the net force experienced on a charge due to electric and magnetic field. Clear? So this is about the magnetic effects of electric current, in which we already cover the all important concepts once again for your revision purpose, and for the detailed study you can refer to the previous video lectures that sent to you. Okay, so try to solve numericals based upon these concepts. Okay, thank you.